Gnanam Paramam Dheyam. Knowledge is supreme.
Recall that in the last couple of lectures we have been studying special polynomial, namely x power n minus 1. This is and therefore we are studying the cyclotomic field extensions. So the assumptions are k any field, and n was, remember that n is non-zero in k. That means characteristic of k and n, they are co-prime, and then we have got a extension, field extension out of this, which is the splitting field of this polynomial. And remember that mu n k. So the mu n of kn, we found this kn is a splitting field of this polynomial x power n minus 1 over k, and this is therefore a subgroup of this, which is cyclic because we know multiplicative subgroup of a field is cyclic, and we want to now prove, and what we want to compute now is we have noted that this field extension is a Galois extension, and we have also noted that this field is, as a K algebra, it is generated by zeta n, where zeta n is a primitive nth root of unity. That simply means this is an element of order zeta n equal to n. This group has order n, and this zeta n is a generator of mu n k power round bracket n. And what we have noted so far is that the Galois group of this field extension, so we know the order of this Galois group. This is simple, so it is k adjoined with zeta n over k. This is same thing as the degree of the field extension, because we have checked it is a Galois extension, and what is more important is n is not 0 in k, and this is by degree of minimal polynomial of zeta n over k. We don't know what the minimal polynomial is, but we have proved that this Galois group, there is a canonical injection from this group to the group of units in the ring Z mod n, and this is true for arbitrary field k, and this is injective group homomorphism. And now we want to prove, this is what we want to prove, in characteristic 0 case, that is k equal to q case, this is an isomorphism. This is an isomorphism of groups. That is what we want to prove today. And once we prove that, then we will know the Galois group of this is precisely Z mod n cross. and we know the order of this group, so that will be phi n, and therefore Galois group will have order phi n. This is of order phi n. Phi is the ordered Euler's torsion function. So this is what we want to prove today. So we want to find what is the minimal polynomial of zeta n over q. So we are in a characteristic 0 case, and now we want to find minimal polynomial of. So the theorem we are going to prove is the following. So theorem, I will recall mu zeta n over q. This is nothing but phi n. So recall that what is phi n? We have and this is enough because we have noted that this. So recall first. Let us recall. So from this polynomial x power n minus 1, we have this is the product zeta in mu n. Whether I write mu n c, that is also enough because all the roots we are in q power round bracket n. So this is x minus zeta, and because this is cyclic of order n, these I have grouped it together and I have written it like this: d divides n, and then product order zeta equal to d x minus zeta, and this we have called it phi n. So it is clear that the degree of phi n is the number of elements of order d in this cyclic group of order n. So therefore this is nothing but phi of n. So this is phi n, and we are going to prove that this polynomial is precisely the minimal polynomial of zeta n over k. Remember that zeta n is a primitive nth root, therefore the order of zeta n is n, therefore this is phi d, not phi n, this is phi d. So number of elements of order n are precisely phi n, zeta n is one of them, and what is phi n? Phi n is phi of n is product order of zeta equal to n x minus zeta, and zeta one of them is zeta n. Zeta n is one of the linear factor which will appear there, and we are interested in this polynomial and we want to prove that this is irreducible over q. That is what the assertion is. Alright. So to get a feeling, I am going to do first a particular case. So first of all, note that when I say irreducible over q, because this is a monic polynomial. So we have also noted, remember last time we have noted that all these polynomials has coefficients in z. So they are indeed polynomials in zx, and this is contained in qx. And because they are monic, irreducibility over q or z, they are same, or z are equivalent because of the Gauss lemma, that because z is the UFD and q is the quotient field of z. So monic polynomial over z is irreducible over q if and only if it is irreducible over z. So we will prove that it is irreducible. Okay, so over z, and that will prove it is irreducible over q also. So okay, for example, I will prove this for when n is a power of prime. Suppose n is p power alpha. This is I want to do this for feeling and also to get understand what is going on, and that is how it was proved in the history also. First it was proved for n equal to power of a prime, and then for arbitrary n. So we are adopting the same thing. So what is phi of p power alpha? So this polynomial is nothing but we have to look at the polynomial x power p power alpha minus 1 and divide by x power p power alpha minus 1 minus 1. This is this. That is very easy to calculate because you see these are the it's only one prime is involved. So the orders are either p power alpha or lesser power, and the lesser power when you group it together they will form this polynomial. So therefore this is clear. And now that means what? That means I want to cancel this factor here. So that means this is nothing but x power p minus 1 times p power alpha minus 1 plus so on and so on plus x power p power alpha minus 1 plus 1. This follows from the fact that, so you see you call this x power p power alpha minus 1 to be y. So this is y minus 1 and this is y power p minus 1. So we are in this, to write this we have used the following formula which is well known. We have used that if I have y power m minus 1 divided by y minus 1, this is nothing but y power m minus 1 plus y power m minus 2 etc. y plus 1. So that is what we have used. So that is the reason. So this is y, so this is y and this is p minus 1 because this is y power p and so on. So you have this, but then further now this equation. So I want to write this is phi power, this is phi p alpha x, this. Now in this equation, in this polynomial equation, I am going to put x equal to x plus 1. Instead of x, I am going to put x equal to x plus 1. So what will I get? I will get phi p power alpha x plus 1 equal to, now instead of x I have to write x plus 1. So that will be, or I could have done directly here. So that is nothing but x plus 1 p power alpha minus 1 divided by x plus 1 power p power alpha minus 1, but this is same thing as I want to read. Now when I expand these polynomials by binomial theorem, and so the top degree term here will be x power p power alpha and the constant term will be 1 power p power alpha is 1 and this 1 will get cancelled and the middle terms will have coefficients divisible by p because they are binomial coefficients of this p power alpha. So the middle coefficients are p power alpha, choose r, but all these guys are divisible by p. So when I read mod p, all the coefficients will vanish. So I am going to read mod p, and similarly the down polynomial, that will be x power p power alpha minus 1. This is the only term will remain, and instead of writing equality I will then write congruent to mod p. That means I am reading this in the ring Z mod p x. So that's what will happen. So we have this equation. I will write it once more. The equation we have is phi p power alpha x plus 1. This is congruent to this is x. So this is x power p power alpha minus 1, which is So cancelling the power, you will get x power. So this will p power alpha, I will take it out. P power alpha minus 1, I will take it out. So it is p minus 1, p power alpha minus 1. And this is mod p. Mod p. So now we are working in this ring, that means ZPX. So these two polynomials are equal in ZPX. Therefore, even after putting x equal to 0, they will be equal. So what will be phi of 1? So phi p power alpha 1, this is equal to x equal to 0. So this is equal to p, multiple of p. This is multiple of p. So because when I put x equal to 0, this side is 0, that means it's a multiple of p. But actually it is, I don't need what it is, it's a multiple of p. It belongs to ideal generated by p. Actually it's exactly equal to p. That I would just ask you to check. Exactly equal to p. Now, why am I doing this? I want to use Eisenstein criterion. So, remember here. So, to prove phi x is irreducible, phi p power alpha is irreducible, I will prove that the translated polynomial is irreducible. I will prove that phi p power alpha x plus 1 is irreducible. For that, I need to use Eisenstein criterion. For irreducibility of the polynomials in Zx. So what we need to check? We need to check that it's a monic polynomial, which it is. Also we need to check that the middle coefficients, they belong to the ideal generated by p, and we need also to check that the constant term is not in p square. So this is the constant term which is x is at x equal to 0, it is p. So it's not in ideal generated by p square. So this is not in ideal generated by p square. It's not a multiple of p. So I can apply the Eisenstein criterion and conclude that, so implies phi p alpha is irreducible in Zx and therefore Qx, and hence in Qx. So that proves it is irreducible for p power alpha. In fact, I just want to make a historical comment here that in fact because of this, Eisenstein proof is the Eisenstein criterion, because to prove this p power alpha cyclotomic polynomial is irreducible, Eisenstein have discovered this Eisenstein criterion. Now we go to the general case. The general case, so we have this polynomial phi n. So proof of irreducibility of phi n in Zx in a general case. So suppose it is not. Suppose phi n is not irreducible. That means phi n factors. But I know one of the root is zeta n. One of the root is zeta n. So one of the irreducible factor of phi n will be mu of zeta n over q. And the other factor I am calling it g with G in Zx, and mu n, we know mu n q, this is actually a polynomial in Zx. Same thing, because mu n is a polynomial actually a priori over q, but mu n is a divisor of this, and the division algorithm tells you this is actually in Zx. In any case, it is like this, and we want to get a contradiction, or we want to prove G equal to 1. That is what we want to prove. All right. So I will claim, we claim that this is the claim I will prove first, that if I have any prime number p, for every prime number p which is a divisor of n, or not divisor of n, and I will call, to simplify the notation, I will simply call mu equal to mu zeta n over q, and instead of keep writing zeta n, I will write zeta n equal to zeta. For every prime number p, I know that this what am I claiming? For every prime number p which doesn't divide n, if x is a 0 of mu, then x power p is also 0 of mu. If x is a 0 of mu, then x power p is also 0 of mu. This is what I want to prove. Okay, so let us finish up this proof, and then we will complete the proof. How does this imply that G equal to 1? So x is a 0 of mu, and I want to prove, so this is to prove mu of x power p is also 0. Okay. So suppose it is false, suppose this is false, suppose mu of x power p is not 0, but then the x power p must be 0 of, we know, if x is a 0 of mu, then it is a 0 of phi n, then x power p is also 0 of phi n, because x power p power n is also 1, because x power n is 1. So therefore, in any case, we know that phi of n of x power p is 0, but this phi of x power p, pn, we have written it as a product of mu and g. So this is same thing as this. But this is not 0, we are assuming, therefore this has to be 0. So we know then g of x power p is 0. But that means this x is a 0 of the polynomial g substituted instead of x power p. Because when I put capital X equal to small x, it is x power p. So it's a x power p is a 0 of this. So that means what? This here is a polynomial g is also in Zx, so this polynomial is also in Zx, and this polynomial, when I put x equal to capital X equal to x, it becomes 0. Therefore, and mu is the minimal polynomial, therefore mu has to divide, mu divides g x power p in Zx. This is what we got by assuming that it is x power p not a 0 of mu. Alright, but now I am going to read mod p. Remember, we are proving the assertion for prime numbers p which is not equal to, which doesn't divide n. So we have, what we are doing is here, it is Zx here, then Z mod px is here. This is a natural map when we are reading coefficients mod p, and there was phi n here, and that phi n we have written it as mu times g, and that will go here phi bar n, which is mu bar g bar, where bar means reading coefficients mod p. Okay, first note that we know that the roots of phi n are distinct. That we noted because n is co-prime to the because phi n is a factor of x power n minus 1 and x power n minus 1 has distinct roots, therefore phi n has distinct root, and the same assertion carries over here because this p is co-prime to n, therefore this phi bar n, which is a divisor of x bar power n x power n minus 1 bar, x power n minus 1 bar, and this polynomial also has the distinct roots because n is co-prime to the p also. So therefore phi n has distinct roots, therefore there is no root common between mu bar and g bar, and our contradiction will be okay. So note that phi bar n has simple zeros. Okay. Now, what do I know about z mod p? Remember that if I have any integer a, then we know that a bar p bar is mod p. A bar p equal to a bar, because it's a group, it's a cyclic group of order p minus 1, and therefore raised to p minus 1, a bar raised to p minus 1 will be 0, will be not 0, 1 identity, therefore a bar power p equal to a. So that we go. Therefore, when I now put in this equation, this is an equation in z mod px, so I am going to put in that equation x, look at g of x power p and take the bar of this. Now this power p, I claim this is same thing as gx bar power p, that p will come out because characteristic is p. So when I write the equations and all the coefficients are, I can write as p powers, and therefore I will take the bracket out, therefore it is this equation. So therefore when I read mod p, I have this equation. So therefore look here that because we noted that mu divides the g of xp, but so therefore mu bar will divide this in zpx, but that means this mu bar will divide g bar power p. So that is mu bar will divide g bar power p, but that will mean that I don't know whether mu bar is irreducible now because we have gone mod p, irreducibility might be disturbed. But in any case, every prime factor f bar of mu bar has to will divide g bar power p in z mod px, but because it is prime, therefore f bar will also divide g bar in zpx, but then that contradicts because we know, we have proved that mu and g don't have any common root. So this is a contradiction. Since mu bar and g bar have no common zero, because this f bar is a factor of mu, therefore if you take the 0 of f bar, that is a 0 of mu, and we have proved that is F bar divided G bar. So G bar will be also 0 of the 0 of F bar will also be 0 of G bar. So that is not possible. Therefore, we get a contradiction. Therefore, what we proved is, if x is a 0 of, we have proved our claim. I will just show you the claim. If x is a 0 of mu, then x power p is also 0 of mu. All right. Now, therefore, and remember now only the last part, that is, so I want to apply this to the following. Now, we know any primitive root, any other generator of mu n c, zeta is one of them we have written. So if you take any other, it will be power of zeta, and which power? That should be co-prime to n. Any other generator of this is of the form zeta power m with GCD of n and m 1, and they are all roots of, they are precisely all roots of phi n. So therefore, the zeta power n, m looks like zeta power p1 to pr, where p1 to pr may be repeated, where pi's are prime factors of m and m is co-prime to n. Therefore, these pi's don't divide n and may be repeated. I just may be repeated, but doesn't matter. So what did we prove? If zeta, we know zeta is a root of mu, then zeta power p1 will also be root of mu. This is what we proved. This is also 0 of mu. And then successfully doing this, then zeta power p1, p2, pr, they are all zeros of mu. So that means every other element of every other generator of this group is also 0 of that, but that means every other root, every 0 of phi n is also 0 of mu. So that, but mu was a factor of phi n. So there is no other way, because the degree argument will tell you phi n has to be mu, and that means G is 1. This is what I want to prove. We wanted to prove this. So that completes the proof that phi n is irreducible over Z and therefore irreducible over Q, and therefore the Galois group of Q power round bracket n over Q is nothing but Zn cross. After the break, I will make some more comments about this Galois group where the characteristic is not 0 now, and this case will be different from the characteristic 0 case, because essentially because the finite field, the Frobenius map is a generator for the Galois group, and therefore Galois group is cyclic, and this will make a difference in the argument. So we will continue after the break.